So can you see my screen now?
Yeah, we can see it.
Okay. So let's get started. If anyone has any questions, you can ask it directly. And here is it's my pleasure to give you a talk. And our today's topic is DGREC, Graph Neural Network for Recommendation with Diversified Recommendation. And this work is finished during my last internship in Embedding group. And our code is open source, and you can check it online. Okay, I will have a special slide to introduce myself. Oh, okay. And actually, currently I'm a PhD student in the University of Illinois at Chicago and supervised by Professor Philip Yu. And previously, I obtained my bachelor's degree and master's degree at the University of Electronic Science and Technology of China. And it is in Chengdu. And I think Haolun may be familiar with this university. And originally, I was born in China, in Xingtai, actually a small town near Beijing. And my research direction is mainly on recommender system, and there are many aspects of recommender system I'm researching on. For example, there are lots of information retrieval tasks, such as recommending items to users or recommending groups to users. So these directions are all within the recommender system. And also there are many kind of evaluation metrics in recommender system, and that I mainly worked on. And the main research direction I'm working on is the accuracy, and this is the most important matrix. And also this paper works on the diversity of recommender system. This is another very important but seldomly discussed problem. And my second direction is graph neural network. And usually I focused on the application of graph neural network, such as its application to recommender system or its application to fraud detection. And here I will give you an introduction on how I see recommender system. And the input of the recommender system is historical user item interactions. And the output will be a list of items for each user. And actually, there are mainly two kinds of methods. The first one is collaborative filtering based method, and this method indicates to recommend items based on the user's historical interactions. And the second kind is content-based method, and this method usually is to recommend items based on user or item features. And from the results, and I mainly worked on the collaborative filtering based method. For example, if we have a set, we have 4 users and 4 items in the data set. And if the users has purchased the item, and we will have a matrix that on this position, it will be 1. For example, user 1 has purchased item 1. So here will be a score 1. And if users did not interact with those items, and we will have a score 0. And this is usually for implicit feedback, which means such as a click or view or add to cart, this kind of behavior. This is called implicit behavior because actually we do not know whether users click that item indicate whether he likes that item. Maybe he does not like that item. We only know that he clicked that item. And also, if we have the explicit information, for example, if we have the user's rating score to the items, and we will usually replace the implicit signal to explicit feedback. For example, we can implicit 1 to the specific rating score that user 1 gives to item 1. And from my work, I usually transform the historical user item interactions to a biparty graph. And for each user, we will have a user node, and for each item, we will have an item node. For example, correspondingly for user 1, because user 1 has interacted with item 1, so we have an edge between the user 1 node to the item 1 node. And we will do not have an edge between user 1 and item 2 because he does not purchase item 2. So in this way, we can transform the historical user item interactions to a biparty graph. And then we can apply graph neural networks on this biparty graph to obtain user and item representation or user and item embedding. After we obtain their embedding, we can compute the preference based on the dot product. And here, I will introduce a general recommendation framework. And actually, there are many steps in a general recommender system in industry. The first step is retrieval. And the retrieval aims to retrieve like thousands of items from the millions of items in the database. So usually we will have a multi-row retrieval, and each row retrieval depends on different kind of methods. And some popular retrieval method includes the popularity or rule-based retrieval method or model-based retrieval method. So after we got the items from the retrieval, and we already have a scoring function, because the retrieval are based on different kind of roles are based on different kind of roles. So we already need to compute the score based on different kind of roles, and to combine them together to get a rank list. So after we compute, we will have a model to compute the score for all the items, and then we will have a re-ranking procedure, which means after we ranked based on the scores, actually that may not fulfill our desired property. For example, if we want the list to be more diversified, or if we want the list to be more fairness, we can apply a re-ranking procedure, which means we re-rank the item list with the desired property. And then I will have an introduction on graph neural network. Actually, this is the main function of graph neural network. And for graph neural network, we usually have a graph, right? And for each graph, for each center node, we know its neighborhood, and the n represents the node with neighborhood. And for computation layer of graph neural network, it consists of two layers. The first one is AGG. It is an aggregator of neighborhood information, such as the max pooling or weighted average. Because in real life graphs, usually for different kinds of nodes, the number of their neighborhoods may be different. So we can see the AGG function, something like a pooling layer, to pull different number of neighborhoods to one representation. And then we will have a combination computation, which combines the neighborhood information and the center node information, such as we can use a linear layer addition, and the different kinds of combination of the aggregation function and the combination function, we can get different kind of graph neural networks. And in the graph neural networks computation, we usually follow the message passing computation, which indicates that for each graph neural network layer, we will compute a message passing to pass the node embedding to the center node. And then we will update the center node embedding based on the graph neural network computation rules. And so for each step, we only message passing the center node's direct neighborhood information. And if we stack several graph neural networks together, for example, in this case, we stacked 3 layers graph neural network. In the first step, we will message passing the direct neighbors representation to the center node. And at the same time, this 2-hop neighborhood also pass the information to its 1-hop neighborhood. So on the second graph neural network aggregation, even though we only aggregation from its direct neighborhood, but it will also aggregate, but at this time, it contains the information from a second-order neighborhood. So the inference scope of a graph neural network is predefined based on the layer number. So a 3-layer graph neural network, for each center node, we will have an inference scope of its 3-hop neighborhood. And then actually, currently the most methods are based on the accuracy-based recommender system, and it will lead to several problems. And I list the 2 that I think the most severe here. The first one is the information cocoon, or called filter bubble. For example, this is a reality, and we are here, and we are surrounded by all kinds of information, all kinds of opinions. However, as a recommender system works like this, accuracy-based recommender system works like this. The more you interact, the more similar items the recommender system will recommend. So after several steps of operation with the recommender system, and all the there are all the platforms provide you the information such as Amazon, Netflix, and gradually you will see that you are stuck in a filter bubble. You are only see the thing that you trust. And actually this drives people crazy. This makes people cannot classify whether what is true or what is not true. It only makes you trust what you see. So you will become stubborn and more stubborn on your own opinion. So that is the problem of filter bubble. And the second one is the negation of long tail items. And usually in all the recommender system datasets, we will observe a long tail distribution of all the items, which means very few products they receive very high attention and they are frequently purchased, but a lot of more products maybe they are very exciting, but they are not recommended or they are not previously exposed to the users, so they are seldomly purchased. So there are maybe a lot of good products here, but we do not discover them. And usually the number of the long tail products, this usually consists of a very large number. So as I previously introduced for general recommendation framework, we have several steps, the retrieval, scoring, and re-ranking. And actually currently we have some method in diversified recommendation, and it can be classified into two categories. The first one is re-ranking based method, which most researchers fall in, such as DPP, MMR, and DOM. And they aim to diversify the recommendation list in the re-ranking procedure. And very few work focused on the retrieval procedure. And previous only one work named the DGC, and they focus on the retrieval procedure. And our method DGREG also focus on the retrieval procedure, because we think that if we do not retrieve enough diversified items, even though you're re-ranking it to get the desired property, it will not be a desired result. And next, to understand DGREG, we need to understand the key idea on the submodular function. What is submodular function? A submodular function is a function defined on a set with diminishing return property. And this diminishing return property seems maybe not very easily to understanding. So this is the equation. For example, we have a set A, and if set A is a subset of set B. And in this case, if we add a new item V to the set A, and the gain on this function will be larger than the gain on we add the new item to set B. And if a function satisfies this property, we call this function a submodular function. And here I give a very interesting example here. And is that, for example, this is example, we have 3 locations, and we also have a square to cover. If we give one location, we will cover a square, and our function is to count the covered space. For example, if previously we have a set that only contains the location 1, and we have another set that contains location 1 and location 2. So if we add a new location 3, and we will obtain different kind of gains on these two kinds of subsets. For example, for the gain, adding location 3 to the subset to the first subset, and the gain f1 and 3 minus f1 will be the black square and the plus the red square, because we are gaining more space compared with only location 1. But if we add the location 3 to a subset containing location 1 and location 2, actually we are gaining only the black area, because the red area has previously been covered by the location 2. So here we can see that the gain we obtained is smaller by adding the item to a subset that contains more items. So in this case, our function that counts the square of the covered area will be a submodular function in this case. And also compared with submodular function, they are modular function. Actually, usually most of the equations used in our life are modular functions. Modular functions, which means there is no diminishing return property, and the gain adding new items to the set A will be always equal to the gain adding the new item to set B. For example, also in this case, if we count how many locations have you added, and the gain will be always the same by adding a new location, because the gain will be always be 1. So in this case, if the function is counting the locations, and the function will be a modular function. And this is a very interesting property by considering what kind of a function is submodular function, or what kind of function is modular function. And from our idea is that what can submodular use for diversification? Is that, for example, in a usually way for the graph neural network aggregation, and for each user, it will have a lot of historical interacted items. And for the previous method, we direct aggregate all the neighborhood information to the user's representation. And if, for example, in this case, the users purchased 2 books and 1 computer, 1 phone, and 1 necklace. If we directly aggregate the information to the center node, the user's representation will be more similar to books rather than the necklace, because the books constitutes a large number, and he will aggregate more information from the books. And the necklace information will be overwhelmed by the frequent purchased items. So in this case, the user's embedding could not reflect the necklace information. So in our assumption is that we should select a subset of the user's neighborhood information to represent all its neighborhood. For example, we know the embedding space of all the items, and then we will select a subset of the items, such as we select a phone, a book, and a necklace, and then we aggregate only on the 3 items. And in this case, the impact that the user purchased the necklace is enlarged, because in previously it will be overwhelmed, but now we select it out. So the key here is how can we select a subset of items that obtain the diversity property. And so we use a submodular function through the selection. And the submodular function computes like this. It mainly computes the cumulative similarity between all the items and the similarity and the selected items. And the similarity can be measured in different kinds of ways. And here actually we measure it by a Gaussian kernel with the theta as a hyperparameter to tune. And then another problem is why this function is a submodular function. And we can, so there is a equation here to easily understand. For example, if we have a set A, which is a subset of set B, and if we add a new item n to the set A, the gain will be the FA plus n minus FA, right? And if we insert this function, and we know that this function actually will be the cumulative sum between the max between the if the new item n will have a larger similarity with items, and we will obtain the similarity. We will get the max will be the similarity between the item and the new added items. But if the new added item is not similar to the previously selected ones, and the result will be exactly the same as previous. So in this case, we can simplify the equation as this one. It will be a max between 0 and the similarity between the new items minus the max similarity of the original selected items. So this will be greater than the case in a bigger subset B, because if A is a subset of set B, and then all the nodes in set A will also belong to the node of set B. So there in some case that for some nodes in V, and the similarity of on the set B will be larger than the set A. So in this case, the gain obtained from adding this new item will be smaller. So in this case, this equation also equals to the the gain, adding a new item to set B. Yeah, this procedure seems a little complicated, and if you do not understand, then we can discuss here. And another observation is the layer attention. Why do we propose the layer attention here? Is because that for each user, and we know it's purchase items, and for the users to hop neighborhood, it will be the users that has co-purchased items with the original user. And for the 3-hop neighborhoods will be the items that the co-purchased users, what they also purchased. So intuitively, we know that if we have higher order attention, and we will get a diversified representation because we are getting more and more items from the user's interest. And the items will not actually the high order items may not have the same interest with the original user, because after several layers of hops propagation, and the interest may be also they are diversified, the interest may be not exactly the same as the original user. So the embedding learned from different layers actually represent different hop neighborhoods. And items in high order layers are more diverse, while at the same time they are also less relevant to the center user. And the different kinds of layer combination strategies may lead to different kinds of results. And usually for a graph neural network, we will, for example, if we have a 3 layers graph neural network, we will aggregate all the nodes within 3 hops neighborhoods and acquire the central node user node embedding. And here we propose a layer attention module to attention on different kinds of layers output. For example, for each layer's aggregation, we will have an output to represent the center node. And for 3 layers, we will have 3 layers output. And we use an attention module to calculate a weighted sum based on different hosts of neighbors representation and obtain the user's embedding. And another observation from our experiment is the long tail distribution of items of each category. And this is the illustration from the Taobao dataset. And it shows a very heavily long-tailed distribution, which means that very few categories have a large number of items, while a large number of categories do not have much items. And which means if the samples with long-tail categories are easily overwhelmed by popular categories. So in this case, if we measure the diversity based on the category, and most of the categories will seldomly be recommended to the users. And to mitigate this problem, we propose loss reweight. For example, usually we compute the loss in recommended system, we compute the pairwise loss, which means if the user has purchased an item, and we compute a loss based on the user item pair. If the user seldomly purchases the item, or if the item belongs to a long tail category, and we can increase the weight on this loss. And if the user frequently purchases the item, or the item belongs to a very popular category, and we can add weight to make the loss smaller. And in this case, we can enlarge the influence that user purchased on long tail categories. And here we use the class balance loss to achieve this property. And the motivation is very easier, and is that we directly assign a weight before each pairwise loss. And the weight is computed as follows: it's 1 minus beta divided by 1 minus beta exponential by the number of items belong to the category. And beta is our hyperparameter for tuning. And this equation, I illustrate the result on this equation on the left figure. And we can see that if beta is equal to 0, and our class balance term will always be 1. And in this case, which means we do not add any loss rebates in this case. And if we gradually enlarge the beta, and we can see we will obtain a line that with the number of samples increased in the ground truth class, and our loss will be diminished. And a larger beta actually indicates the line will be sharper, which means we will have a larger diminishing property. And by applying the class balance laws, and we can obtain different kinds of weights for each user item pairs. And this aims to focus on the training of the long tail categories. And we test our experiments on two datasets. One is Taobao dataset, another is Amazon Beauty dataset, and several kinds of popular baselines, including the popularity and the most widely used MFBPR and several graph neural network-based methods. And here is overall result. We can see that for the actually for the comparison of diversified recommender system, we should consider two aspects. One is the accuracy aspect, which is measured by the recall and hit ratio, and another one is the diversity matrix. And in our work, we measured it by the coverage. And the coverage indicates that how many categories have we covered. For example, if our DG rec is 39, indicate that if we recall 100 items, and we will coverage 39 categories. And from the result, we can see that usually the light GCN achieves the best accuracy, but at the same time, their coverage is the lowest. And the previous work, without considering the diversity, they usually face the accuracy diversity trade-off, which indicate that if they have a higher accuracy, they tend to have a lower diversity. And for our work, we can see that we can achieve the highest diversity, and at the same time, our accuracy also performs pretty good. And it is the same on the beauty dataset. And oh, okay. Do you have any questions, Rebecca?
Yeah, I had a quick question. How do you apply GCN on the bipartite graph? Do you kind of just assume that there's one node type? Or how do you use it to make recommendations?
Oh yeah, for GCN, we usually for GCN we can see that actually you can see that for the application of GCN we see the user item as only one type of node, and directly applies the aggregation on the bipartite graph.
Gotcha. Okay, thanks.
Yeah. And usually in recommender system, we treat it in that way. Not only in the GCN, but also the light GCN proposed in recommender system. It's because that in the training of recommender system, and we actually the user node only has connections with the item node in the bipartite graph. So usually we want to train the embedding to make them similar, which indicates that if they are connected, just make them similar. So during the whole training procedure, you can see the user and the item embedding, they are within the same space. So in most of the cases, we treat them as one type of node.
And then I have another question about what you were saying with coverage. So it seems like you define like a category or a class. I'm not personally familiar with the Taobao and the Amazon Beauty dataset. So do they come with their own categories, or do you define them based on some sort of like long tail distribution?
Oh, the coverage, they have the ground truth. They have their own, for example, for the two data sets, they know for each item what the category it belongs to. So we directly use the ground truth information to compute the coverage.
Gotcha. Thanks.
Yeah.
Yes, sir. I guess I have a follow-up question. So when you count the category, do you only consider one item belongs to one category? Because I think there are some data sets that have multiple tag situation. Like for instance, in movie lens, one movie can belong to multiple genres. So like, how did you do that here?
Yeah, usually we do not consider one item only belongs. If based on the ground truth data set, if the ground truth data set, we know the item belongs to several categories, and we will count all the categories.
Okay.
Yeah.
Okay.
Yeah, and we will count. And the result is we only counting the unique categories. For example, if the record items say several items belong to the same category, and we only count one.
Okay. Thanks.
Yeah. And to better illustrate the result, and I further make the result into a diagram. And the x-axis is to measure the accuracy, which is measured by recall as 300, and the y-axis is the diversity, which is measured by coverage as 300. And we can actually, from the picture, we can see that the model that reaches the uppermost, the upper right, will have the best accuracy diversity trade-off. And we can see the like GNN is here, and it is a traditional accuracy-based method, and it will achieve very high accuracy, but at the same time, its diversity will becomes very low. And for the work previous, our work focused on the diversity, such as DGCN is for here, and our method achieves the best trade-off, and it is here. And here we make an avalanche study on the top-level dataset by removing the 3 modules step by step. And here is one very interesting finding is that, for example, if we remove the submodule selection and the layer attention, and usually our accuracy will increase, and at the same time our diversity will drop. But if we remove the loss reweighting, it will have a very big impact. And the recall, the accuracy, and the coverage will both drop. And for a reason for that is that I think because the loss reweighting compute directly on the loss, and the model is optimized towards loss, so it is highly impactful. It is highly impactful because for the training of the model, for the loss reweighting, it will directly influence on the layer attention module. So here for recommended system, I think this loss reweighting module it has a very high impact, and we can test it further. And here we show the effective of different kind of modules. The first one is the effective of submodular neighbor selection. For the function we used, the submodular neighbor selection, we have 2 hyperparameters. The first one is the sigma, which measures the distance, which measures the similarity computation. If the theta is smaller, and the model will be more sensitive to the distance of items pairs. And the second one is a predefined selected item k, which means how many neighborhoods are we selecting. If k is equal to 5, which indicates that for each node we only consider its 5 neighborhoods to select in the submodular selection procedure. And in this case, we can see that actually the theta function, although the theta changes in a very large range, the result will not. The result is pretty stable. It will not jump higher and lower in a large margin. So the model is not very sensitive to the theta function because our model selects the neighborhoods in a greedy method. So it is usually based on the rank, not the specific value. And for the key value, we can see that if we add more items in the neighborhood, and the models will consider more and more diversified neighborhood, and our diversity will increase, and at the same time, the accuracy will drop. And here we show the effective of the layer attention module proposed in our neighbor, and we compare the layer attention module with the mean computation. And we can see that if we directly use the mean computation with the increase of layers, and the accuracy drops greatly, and the diversity increases greatly. And this is not the desired property, because which indicate that the model is overwhelmed by the high order neighbors, and the high order neighbors also they achieve very high diversity, and their accuracy, the drop is very great, and so the mean computation is not a very good choice. But if we replace the mean computation with our layer attention, and we can see our accuracy actually stays pretty stable. And for more layers, and the coverage is also reaches a very high. It reaches a very high range. And the last part is for the loss reweight hyperparameter, which means beta. And the beta influence the loss reweight decaying effect. If the beta is larger, and we will have a larger decaying effect. And so we can see that if we gradually change the beta, even a small change on the beta, and our model will fall into a different kind of position. If the beta is larger and we are diminishing more on the weight of popular items, and the model will be trained towards the long tail items. So in this case, the diversity will increase greatly. And also it is at the cost of accuracy. So in this case, we can see that we can use the beta hyperparameter to achieve the accuracy diversity trade-off. And finally, I want to discuss the advantage and disadvantage of our method. For the advantage that we achieve the best diversity of graph neural network-based recommender models. And actually, these three models can be applied easily to different kind of graph neural networks. And the second one is the trade-off between accuracy and the diversity can be easily tuned by the beta hyperparameter. And the third one is actually our code is using the DGL as a backend. And DGL is a graph neural network training platform provided by the Amazon. And the training is very fast as long as the memory can hold the whole graph data, no matter it is on GPU or it is on CPU. And also the disadvantage is that our method is not very effective when the category number is small. Because when the category number is small, actually we could not differentiate the items diversity based on the category. For example, if in the dataset we only have 6 categories, and if you recall at 300, nearly all the category will be recalled out. So our method is not effective when the category number is small. And for our experiment, also we only consider the diversity in items category, which is also a limitation in this paper. Because there are a lot of data sets that they do not have items category information, and how to measure the results on those data sets is not provided in the paper. Yeah, and that's the paper. And do you have any questions?